Welcome to our lesson on limits and continuity in calculus. Today, we'll explore the fundamental concept of limits, understand their formal definition, and see how they relate to the continuity of functions. Let's start with an intuitive understanding of limits. A limit describes how a function behaves as its input x approaches some value a, even if the function is not defined exactly at a. We write the limit of f of x as x approaches a equals L, which means as x gets arbitrarily close to a, f of x gets arbitrarily close to L. The key idea is that we care about values of f of x near a, not necessarily out of itself. Let's visualize this with a simple example. Consider the function f of x equals x squared. If we want to find the limit as x approaches 2, we look at values of f of x when x is close to 2. As x approaches 2, from the left, f of x approaches 4. As x approaches 2 from the right, f of x also approaches 4. Therefore, the limit of x squared as x approaches 2 is 4. Now, let's explore the formal definition of a limit, which is known as the epsilon delta definition. We say the limit of f of x as x approaches a equals L if for every positive epsilon, no matter how small, there exists a positive delta, such that whenever x is within delta of a, but not equal to a, f of x is within epsilon of L. Epsilon represents how close we want f of x to be to L. Delta tells us how close x must be to a to guarantee that. The condition 0 less than the absolute value of x minus a less than delta means x is near a but not equal to a. Let's visualize the epsilon delta definition with our previous example of f of x equals x squared as x approaches 2. If we choose an epsilon, say 0.5, this creates a horizontal band around L equals 4. We need to find a delta, such that whenever x is within delta of 2, but not equal to 2, f of x falls within this epsilon band around 4. For this function and this epsilon, a delta of 0.125 works. When x is within 0.125 of 2, f of x is guaranteed to be within 0.5 of 4. If we choose a smaller epsilon, we'd need an even smaller delta. This is the essence of the epsilon delta definition. Now, let's look at some examples of computing limits. Example 1. Find the limit of 3x squared minus 5 as x approaches 2. Since polynomials are continuous everywhere, we can directly substitute x equals 2 into the function. 3 times 2 squared minus 5 equals 3 times 4 minus 5, which equals 12 minus 5, which equals 7. Therefore, the limit of 3x squared minus 5 as x approaches 2 is 7. Let's try a more challenging example. Example 2. Find the limit of the fraction x squared minus 1 divided by x minus 1 as x approaches 1. If we try direct substitution, we get 1 squared minus 1 divided by 1 minus 1, which is 0 divided by 0. This is an indeterminate form. To resolve this, we need to factor the numerator. X squared minus 1 can be factored as x minus 1 times x plus 1. Now we can simplify for x not equal to 1. The fraction becomes x minus 1 times x plus 1 divided by x minus 1, which simplifies to x plus 1. Now we can find the limit as x approaches 1. The limit of x plus 1 as x approaches 1 is 1 plus 1, which equals 2. Now, let's discuss one-sided limits. Sometimes, a function behaves differently when approaching a point from the left versus from the right. This is where one-sided limits come in. The left-hand limit, written as limit as x approaches a from the left, means x approaches a from values less than a. The right-hand limit, written as limit as x approaches a from the right, means x approaches a from values greater than a. A two-sided limit exists only if both one-sided limits exist and are equal. Let's visualize one-sided limits with an example. Consider this piecewise function. F of x equals x plus 2 when x is less than 1, and f of x equals x squared when x is greater than or equal to 1. Let's draw this function and examine its behavior at x equals 1. From the left side, as x approaches 1, f of x approaches 1 plus 2, which is 3. From the right side, as x approaches 1, f of x approaches 1 squared, which is 1. Since the left and right limits are different, 3 versus 1, the two-sided limit at x equals 1 does not exist. Now, let's discuss continuity, which is closely related to limits. A function f is continuous at x equals I if all three conditions hold. First, f of a is defined. Second, the limit of f of x as x approaches a exists. Third, the limit equals f of a. Intuitively, a function is continuous at a point if there is no jump or hole at that point. The graph can be drawn without lifting your pencil. Let's look at examples of continuous and discontinuous functions. First, f of x equals x cubed at x equals 2. F of 2 is 8. The limit of x cubed as x approaches 2 is also 8. Since they match, f is continuous at 2. Now let's look at a discontinuous function. F of x equals x squared when x is not equal to 1, and f of x equals 5 when x equals 1. The limit of f of x as x approaches 1 is the limit of x squared, which is 1. But f of 1 is defined as 5. Since 1 does not equal 5, f is discontinuous at x equals 1. Let's look at the main types of discontinuities. A jump discontinuity occurs when the left and right limits exist, but are different, like in our piecewise function example. A removable discontinuity or hole occurs when the limit exists, but either the function is not defined at that point or is defined differently. This is like our x squared at x equals 1 example. An infinite discontinuity occurs when the function approaches infinity as x approaches, like in the function 1 divided by x at x equals 0. Let's summarize what we've learned. A limit captures the behavior of f of x as x approaches some point. The epsilon delta definition formalizes the concept of getting arbitrarily close. Continuity at a point means the limit equals the function's value at that point. With practice on various functions, you'll develop a strong intuition for limits and continuity. Thank you for watching this video on limits and continuity, essential concepts in calculus that form the foundation for derivatives, integrals, and much more.